So I chose to solve this problem by relying on our knowledge of conservation of energy, one of the big topics we talked about in this unit. And conservation of energy says that the kinetic energy plus the potential energy at all points in this problem should be the same. So for this original point to look at, I'm going to choose the point where the block is over here with an original velocity of 2 meters per second, so it definitely has a non-zero kinetic energy. And what about the potential energy? Well, there's always some gravitational potential energy, but that's not going to change in this problem because the block is only traveling horizontally, so we can safely ignore that for this problem. So the only potential energy we're concerned about is the potential energy of the spring. And since currently the spring is completely uncompressed, it's at its equilibrium length, we can say that the potential energy in the spring is 0. So we can cross out this term. And for my final point, I'm going to choose this point here where the block's speed is 0 and the spring is quite compressed. Now, why do we know this happens? Well, the block comes in with a velocity pointing to the left of 2 meters per second, and we know it's going to push against the spring and go back with a rightward velocity of 2 meters per second. So somewhere along the lines to changing between a leftward velocity of 2 meters per second and going to a rightwards velocity of 2 meters per second, the velocity must have been 0. And that's actually the point where the spring is the most compressed during the entire course of this spring-block interaction. So it makes for a good point to look at in our equation. And at this point, since the velocity of the block is 0, it has no kinetic energy. So we know that the final kinetic energy here is 0. All right, we're making progress. So now I can replace the kinetic energy with 1/2 mv squared and the potential energy with 1/2 k delta x squared, like we saw in the previous video, and plug in those values, and we get that the maximum displacement away from the equilibrium length is 0.141 meters. Great work.